This looks like the simplest game in the world. Heads or tails, 0 or 1, win or lose. That is basically how normal computers store information. A bit is either 0 or 1. But quantum computing starts in the part normal computers do not have, the state before the answer. A qubit is not locked into 0 or 1 before measurement. And that is the first idea I needed to understand before this project could go any deeper. In my last video, I introduced the rebrand and the project. I'm going to be documenting my journey of building a quantum machine learning system for zero-day malware detection. But I don't want this use to end up me talking about big words I barely even understand. So, before the quantum machine learning, before the malware datasets, before the actual model, I first need to answer a specific question. That is, what is quantum computing and how is it different from normal computers? For that, I need the foundation, and this video will help me how to build that foundation. Normal computers uses bits. A bit can either be 0 or 1. That sounds really simple, right? But the way your whole computers move is based on that specific idea. Images, videos, network traffic, and even malwares. It all comes down to patterns of zeros and ones. Normal computers are really powerful because they can change between those states. On, off, 0, 1, true or false, all of them. And there's one really important point you need to know, and that is a bit can either only be 0 or 1, nothing in between. Quantum computers uses qubits. A qubit is a quantum bit, but its rules are slightly different from normal bit. A bit can either be 0 or 1. A qubit, on the other hand, can go in a quantum state where there's some probability of it becoming a 0 and there's some probability of it becoming a 1. This is really interesting because this just shows it's not necessary to be discrete. It could go in continuous ways. But after that, I heard a lot of people saying that a qubit can exist at 0 and 1 at the same time. But even though that helped me at first, I think that is not completely true. That just makes quantum computing sound like magic, while it isn't. So let's go and dive deeper into it and know what's the reason. So basically, the way a qubit moves is it can go in a quantum state where there's some probability of it becoming a 0 bar, right? So before measurement, it is in that state, in that liquefied state where there's malleability. It can either go towards this side or this side. But after measurement, it gives a discrete answer. That is, it can either give you a 0 or a 1. That is really interesting. And this just shows like how wide quantum computing scope can be. So basically, quantum computing is not magic. We just know that now. And before measurement, it is in a state called as superposition. This is a really important concept that is even used in physics. And it just shows in this case that before measurement, it acts in this state where we do not know where it's gonna go. It's in a in-between phase. And after measurement, we get a real discrete answer. So let's talk about the coin game that made this click for me. Imagine you and a robot are playing a hidden coin game. First, the robot takes its turn, then you take a turn, then again the robot takes a turn. And the rules are that you have to flip the coin or you cannot flip the coin. Like, it's your choice. And the robot is not going to show you the coin either. So this way, if after all of the turns, it turns out it's head, the robot is going to win. And if not, and it's tails, then you are going to win. And this gives us like a 50-50 chance of winning, you know? But now imagine you are using a quantum coin instead of a normal coin. Now, whenever you have to take a turn, you can put it in a quantum state where there will be a probability to go on either sides. The robot has took its first turn and put it in a quantum state. Then you're gonna take it. Then the third turn is gonna be the robot again. And it's gonna make either the robot is gonna win or you're gonna win, but there's gonna be a huge difference in the terms of chances. As the last one it was around 50-50, and this is now gonna be 50-50. And this experiment has actually been done that human has played this game with a quantum computer, and this shows how many times the quantum computer won against the human. Entanglement is another concept. I'm not going to dive deep into it in this video because it deserves a separate video on its own. But I'm just going to explain in simple terms so that it makes sense. Basically, imagine this is one qubit and this is another qubit. Both of them have their own quantum states. But if you link them both, this is called entanglement. And this creates way more paths for the qubits to travel in their specific states, and it makes processing a lot faster. So just in simple words, know that when qubits are linked, not just two, when two or multiple qubits are linked, it forms entanglement. Why is this important for cybersecurity? The most obvious answer would be cryptography. Because whenever you think of quantum computing, the first thing that comes in your mind, that is how fast quantum computing is going to break encryption. But it's not the same in this case, in my project. My project is about building a quantum machine learning system for zero-day malware detection. And requires us to answer a more simpler question, that is, using quantum computing, what kind of problems can we actually solve? And more specifically, can a quantum machine learning system help me detect zero-day malwares? I do not have the answer yet, but that is the point of this series, that we go and explore and understand each and every concept and how this will eventually help me build it. And I'm confident in that. So my current understanding is this: quantum computing is not magic. Quantum computing is not a faster computer. And quantum computing is a really different kind of computer. And a good example is explaining it this way is that this is a candle and this is a normal computer, for example, and this is a light bulb, which we can say is a quantum computer. Both of them provide us light, right? But the mechanisms of both of them are really different. I think this is the best way to sum it up. So in the world of quantum computing, the most basic unit is qubit. So before I go towards the next step, I need to first understand what is the qubit, not in some oversimplified way, in a way that it could teach and help me provide you guys with more information about it. If you're interested in cybersecurity, malware detection, machine learning, quantum computing, or just watching a serious project get built from zero, this is where it starts. Follow the journey from the beginning, from qubits to 0 days.